Welcome back. Now, many of you might have thought, true, that fossil fuel reserves are scarce because there's been a lot of conversation in the past decade or so about oil peaking. We'll talk about that in this segment specifically. But in reality, the fossil fuel reserves are actually pretty extensive. So if you look at global reserves to production ratios, so that's the R to P ratio that you see in this figure, they're projected at over 40 years for oil, 60 years for gas, and 160 years for coal. The error bars on those are huge. And that's primarily, you might think to yourself, why? Why is it hard for us to understand how many reserves are left in production? Well, one is, of course, that we've already discussed, is that production is increasing, and it's increasing in some ways that are very predictable and some ways that are not. But the reserves are what's tricky because there's a rate of new discovery which is declining, particularly for oil. But in addition to that, there are new technologies and new methods. Take, for example, multilateral drilling, which has really opened oil and natural gas extraction dramatically in the past 10 years that weren't predictable, that people didn't realize that those technologies would come online. So the reserves number is changing all the time, as well as the production number. But globally, we have hundreds of years of use predicted in each of the major fossil fuel carriers, oil, natural gas, and coal. In the U.S. alone, they predict over 10 years for oil, 10 years for gas, and over 200 years for coal. In China, the predictions are over hundreds of years for coal. So what does that mean? And what does it mean in particular for energy carriers? Well, let's take a look at some of the specifics here. So in this figure, you see these are a couple of figures out of the Department of Energy in the United States. They provide an annual energy review. These are freely accessible, and I grabbed these from the 2005 version of the Department of Energy Information Association. They update them. They're a little bit behind, so they'll be probably up to maybe 2007, 2008 now, so you can get some new data. But the trends are pretty consistent. So what you're looking at are two figures for oil and natural gas. And you see the reserves. In this case, for oil, it's given in billions of barrels. In the case of natural gas, they're given in trillions of cubic feet. The dark black are the reserves. The gray are the production. And then the white is the consumption. And you can see in the U.S. is we are net consumers. The United States has been a net consumer for a number of years. It is predicted to be a net consumer for years to come for oil. Natural gas, you can see again in 2005, the U.S. was a net consumer of natural gas. With fracking, this has changed dramatically. And so you can see the shift from being a net consumer to a net producer. So that's made a dramatic shift in both the cost of natural gas and the production and consumption of natural gas in the United States. OPEC is, of course, the Middle East Association of Countries, and you can see, of course, that as you would expect, that the majority of the oil reserves are located in OPEC, and then you have the rest of the world shown in the last set of bar graphs on each of these two figures. But what it comes down to is, with the exception of OPEC, the rest of the world and the United States are pretty much net consumers of oil and natural gas. If you broaden this definition to energy in general, you'll find that the majority of the countries in the world are net importers of energy. There are very few, but there are some key exceptions, and those are kind of fun to think about. What would be the attributes of a country that is a net producer of energy? And I'll give you that as just a teaser. Go look those things up. It's kind of fun. So this is oil and natural gas. And again, in the United States, coal reserves as of 2003 had demonstrated over 500 or close to 500 trillion short tons. Now, if you take that coal, there are a number of different methods that we can use to extract or convert that energy from the solid phase of coal into a liquid fuel. And generally, this discussion is associated with the transportation sector because the transportation sector is dominated by liquid fuels, and in particular, it's dominated by oil. So the majority of the energy carrier in the transportation sector comes from oil. The converse is not also true. Oil is not exclusively used in the transportation sector. Oil is also used in a number of different applications, including agricultural, refining, plastic products, etc. But the transportation sector is dominated by the use of oil and oil-derived liquid fuels. If you could take all that coal in the United States and convert it into liquid fuels, you could get about 1 trillion barrels of liquid fuel. So we could convert these carriers around, convert them from, let's say, one form to another, and use that in different sectors. So it gives you some idea of what we're talking about here, some idea of what the scales are. So let's keep going. So these are the conventional fossil fuels: oil, natural gas, and coal. Let's talk about the alternatives. These are still fossil fuel feedstocks, and we're hearing more and more about them. Again, we hear a lot about fracking in the United States, but that's pretty much natural gas, so that's not very unusual. Global demand for petroleum, let's anchor ourselves, let's give ourselves a reference, is about 170 quad BTUs. So that's about 170 times 10 to the 15. Quad, as we remember, a quad is about 10 to the 15 BTU. A barrel of oil has about 6 times 10 to the 6 BTU of energy equivalent in that barrel of oil. The alternative fossil fuel feedstocks include oil sands. And oil sands are exactly what the name implies, which essentially is petroleum that's been soaked in sand. And in the United States alone, we have over 80 billion barrels of equivalent in oil sand, located predominantly in Utah, but also in Alaska, Texas, California, and Tennessee. Oil shale is a mineable ore or rock rich in organics and hydrocarbons. So it's heavier in a molecular weight way. It's heavier in terms of just processing. The U.S. has 2.1 trillion barrels equivalent of energy in oil shale. The catch is most of these deposits are located in the Rocky Mountains, which include Utah, Wyoming, Montana, and they are in very close proximity to the U.S. national parks, in particular the Grand Tetons and Yellowstone. So personally, I hope we leave these fuels in the ground because, again, they are very specifically co-located with the national parks. And you can get into the geologic reasons as to why. Yellowstone is also a great geothermal reserve. Again, I'm very hopeful that we will not tap into that access because of the beauty of the national parks. Okay, the Canadian oil sands, which are located in Athabasca, Canada, are the world's single largest hydrocarbon resource. We are mining, the royal we, which is everybody in the world. Canada, specifically, is mining the oil sands. And in the United States, a significant amount of the oil that we import comes from the Canadian oil sands. That extraction process, I can tell you, is very environmentally invasive, requires a lot of water in order to process those oil sands. There's about 2.5 trillion barrels of oil presumed. Again, these are estimates. Located in the oil sands, only about 12% of that is considered recoverable with today's technology. This is, again, why you see these variability in the recoverable versus known resources for the fossil fuels. Because, again, this is how much we can get right now. I guarantee you the number is going to go up. It's not going to go down. What does that mean? We have 2.5 trillion barrels of oil located in the Canadian oil sands. If you could access the oil sands, you could meet the global demand for oil for over 60 years. Now, I just used a simple calculation. I didn't include, population increase, which is significant as we know. But we're still talking over 6 decades of oil use out of just that resource. Okay, so that's a lot of oil. Let's keep going. This is considered a non-traditional or alternative feedstock fossil fuel, I guess would be a better way of describing it. Now let's consider the methane hydrates. The methane hydrates are methane essentially locked into ice at the bottom of the ocean off the eastern seaboard of the United States. The methane hydrates have been estimated at over 20 quadrillion cubic meters. This is over 3,000 times the proven natural gas reserves. Mind you, they're located over a mile deep on the ocean floor. These are in excess of most of what we've demonstrated in terms of deep ocean drilling. 20 quadrillion cubic meters of natural gas reserves is about 60 trillion barrels of oil equivalent. The energy content of the methane hydrate reserves could meet the global demand for oil for over 1,500 years. The methane hydrates is methane physically bound into like an ice form, located off the eastern coast, the eastern seaboard of the United States, on the ocean floor. The methane hydrates, the energy content and the physical amount is estimated at 21 quadrillion cubic meters. That's over 3,000 times the proven natural gas reserves. That's essentially almost 60 trillion barrels of oil equivalent in terms of energy equivalent. The methane hydrate reserves could meet the global demand for oil for over 1,500 years. Again, I just did a simple energy equivalent calculation. So I didn't scale for population growth or increased energy demand on a person basis. But it's still staggering. The number is staggering. If we consider all energy sectors, oil, coal, fossil fuel, renewables, the methane hydrate reserves in energy content alone could meet all energy needs for over 300 years. There's a huge amount of energy trapped or contained within the methane hydrates. However, they're located, again, over a mile deep on the ocean floor off the eastern seaboard. And this would require, extracting the methane hydrates would require a demonstration of a lot of new technology. This is deep water drilling. This is a hydrate, which is very different than an oil. It's under a lot of pressure right now, and it's very cold because it's located on the ocean floor, the hydrates. And extracting would bring these fluids, not really fluids, but would bring this material up to atmospheric pressure, which would be a low pressure and a warming condition. Methane, as we'll discuss in just a few moments, or actually in the next segment, is actually a very high global warming potential gas. So there are a lot of technological concerns, there are a lot of ecological concerns associated with extracting the methane hydrates. So again, if we look at fossil fuel, both traditional and non-traditional or alternative fossil fuels, there are a lot of fossil fuel reserves around the world. They are not scarce. And if we are going to use scarcity as a driver for changing our behavior, for improving efficiencies or the way we use energy, it's not going to happen. That's not a good motivation for change because we're never going to be driven by scarcity if these numbers are accurate. So instead, I want you to think about two things, which we'll discuss next time. The use of these fuels comes at a very high environmental and ecological impact.